Hello everyone, this is Dr. Daya Sagar Chowdary, Assistant Professor, Department of Electronics and Communication Engineering, Aditya University. Coming to today's topic, number systems. So representation of numbers of different radix. So finally, this is the learning outcome, representation of number systems of different radix systems. So we already discussed about decimal, binary, octal and hexadecimal. Not only these four, there are so many number systems are there. And we represent 10 as a base and 2 as a base, 8 as a base and 16 as a base. Not only these four, we can also use the base numbers in the tricky questions like 5 as a base, 9 as a base and 7 as a base. Likewise, we can give like this is a tricky one. Let us see the overview of the number systems. So number systems are fundamental concepts in mathematics, electronics and computer science used to represent quantities. Different number systems serve different purposes such as counting, measuring or encoding data. Understanding these systems helps how numbers are expressed beyond just familiar decimal notation. So let us see what are the number systems and how we use the representation here. So here the representation of the number system. So this is the simple figure that contains the number systems. So here basically we follow the decimal number system. Mostly decimal contains 10. Decimal means 10. That means the digits from 0 to 9 it contains. Also binary number system is there. Mostly we use this binary number system in the computers. So binary number system contains 2. So either 0 or 1 and the radix is 2. Coming to octal number system, so this contains 0 to 7. So totally 8 numbers are there. So 8 digits. So from 0 to 7 we are using. Coming to hexadecimal number system, so hexa is nothing but 6, decimal is nothing but 10. So totally 16. So from 0 to 9 as usually it follows the decimal. As usual hexa means so total 6. So A to F. So A is nothing but 10. B is represented by 11. C is represented by 12. So on up to F is represented by 15. So totally 6 plus 10, that is hexa plus decimal. We call that one as a hexadecimal. So that base is 16 here. So 0 to 9 and A to F. So this is the commonly known number systems in our representations. Now, so let us come to the point. This is the decimal number system. Mostly we follow 10 as a base. So that means the definition is the decimal system is the standard counting system using 10 digits from 0 to 9. So 0 is a symbol and 9 is a symbol. In between all these are symbols. So we have to count like 0, 1, 2, 3, 4 like to up to 9. So it is called base 10 because it is based on 10 symbols. So contains 10 symbols. We already discussed it here. So uses. This system is used in everyday life for counting, doing money transactions and most calculations because it aligns with human finger counting. Because human fingers are 10. So for calculation part, it is very easy when we are using our own fingers. And place values. So each digit's value depends on its position with the powers of 10. Units, tens, hundreds and thousands. Likewise, it will follow. So we know already, so our human fingers are 10. So likewise, position is also very important. So the first position, let us come to the point. So 1, 2, 3, 4. Here the fourth position is the units place and third three position is the tens place and two's position is the hundreds place and one's position is the thousands place. Depending on the position also, it is the position and the value is changed here. What are the numbers it contains? So these are the numbers. So we know already. So from 0, 1, 2, these are the symbols. So in decimal from 0 to 9, these are the symbols. So 0, 1, 2, 3, 4. These are all the symbols. So after 9, so we need to increment. So if we contain, so 0 to 1, there is only one increment. So 1 to 2, there is other increment. So only one increment again. So 2 to 3, this is again one increment. So most of the time we used this symbols, right? So that means recently we used that symbols. Depending on the symbols, see we can use that. So 0, this is 1, this is 2, this is 3, 4, 5, 6. So that means there is one increment from one symbol to other symbol. So that means there is a representation actually. So 1 is represented like this. That means there is a single angle between these two. That means only one angle means, so this representation is 1. And here 2 is simply represented like this. That means it contains two angles. That is why we call this one as a 2. And for 3, this is the representation. That means 1, 2, 3. So there are 3 angles. That is why we call this one as a 3. And for 4, so this is the 4. That means 1 angle, 2, 3, 4. So 90 degrees, 90 degrees. So totally 4. And coming to 5, so this is the representation. So 1, 2, 3, 4, and a small representation here 5. That is the 5 representation. And finally 6. So this is the 6. So 1, 2, 3, 4, 5, 6. So these are the 6 angles. So totally it contains 6. 7 is a little bit. This is the 7. So 1, 2, 3, 4, 5, 6, 7. This is the 7 representation. And coming to 8. So this is the 8. So 1, 2, 3, 4, 5, 6, 7, 8. So totally 8 angles. It contains 8 angles. That is why we call this one as a 8. So coming to 9. So this is the representation of 9. So 1, 2, 3, 4, 5, 6, 7. And this is extension. So 8, 9. So these are the actual symbols in the from the previous days. So now we are moving to our modern technology. We just change it to 1 is like this, 2 is like this, 3 is like this, 4 is like this. So this is a simple representation. Depending on the angles only, we are giving the numbers. So that is why from 0 to 9 it is possible. That is okay. Now after 9 we need to increment 1. So there is no other symbol. If we give so many numbers or so many symbols, it is very difficult to for us to count, to remember, to memorize. So that is why we simply take 0 and 1. So that is why 1, 0 is the next increment, single increment. So this is the 10. So next 11, 1, 1. Again we are placing 1, 1. And 12, 1, 2. And 13, 1, 3. 14, 1, 4. Likewise, we are simply counting one increment after one. That means one symbol to other symbol we are following and according to our number systems. Next, coming to binary number system. So this binary, bi means 2. So 2 is the base here. So we are using within the brackets the total binary number, suffix is 2. Here binary uses only 2 digits, 0 and 1. It is the foundation of all modern computers. As we know, our humans are following the decimals, but computers following the binary number system. Significance: computers use binary because electronic circuits have two states, on and off, which corresponds perfectly to 1 and 0. So here mostly 0 represents the low or off state, 1 represents the on or high state. So this is the representation of the binary number system. So left side, this is a decimal number system, and right side, this is the binary. So this is the representation with 4 bit. Actually, this is the single bit, 2 bits, 3 bit, 4 bit representation. Likewise, we use the 4 bit representation in the binary. So that is why for 0, 4 zeros, 4 bit representation for 0 in decimal, and 1 is 0, 0, 0, 1. So we will check in the next slides, this calculation part, everything in the next slides. So just remember that 1 is 0, 0, 0, 1 is the representation for 1, 0, 0, 1, 0 is the representation for 2, 0, 0, 1, 1 is the representation for 3. So if we observe, the last bit is completely switching from 0 to 1. So 0, 1, 0, 1, 0, 1, 0, 1. Likewise, it is following, and the second bit is following 2 times. So 2 times 0 and 2 times 1, 2 times 0 again, 2 times 1. For third bit, so again it follows 4 times. So 4 times 0 and 4 times 1, 4 times 0 again, 4 times 1. And the fourth bit is 8 times 0 and 8 times 1. So simply it is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. Here 2 to the power of 0 is 1. That is why simply switching next 1 1 1. Here 2 to the power of 1, that is 2. So 2 bits, 2 bit representation. So 2 times 0 and 2 times 1 likewise. 2 to the power of 2, that is 4. So 4 bits zeros and 4 bits ones. And 2 to the power of 3, that is 8. So totally 8 zeros and 8 ones. Just remember this number system, simple number system. Later we will see the conversion. So this is other number system. We call this one as a octal. So octal contains from 0 to 7. So totally 8 symbols. So from 0 to 7. So this is the octal uses 0 through 7 and the base is 8. So simply we represent the octal. So octal, this is the octal symbol and this is the base. Now often used as a shorthand for binary numbers because each octal digit corresponds to 3 binary digits. This is also we'll see in the next slides. Advantages: more compact than binary, making reading and writing binary sequences simpler. That means, so here there is a representation of binary 1001 or 101011. So this is a simple representation in the binary. So this can be represented in octal. So how? So 3 bits can be, we can short the like, so here 2 is the base, here 8 is the base. We can equalize 2 is equal to 2 to the power of 3. That means 3 bits we can group. So that means this is the 3 bits, this is the 3 bits we can group. That means 011, so that is 3 representation in binary, 101, that is 5 representation in binary. So no need to remember all the 6 bits, we can remember 5 3. So likewise we can simplify this binary, the octal number system. So this is the octal number system. So 0 representation in decimal. So octal is 3 bit representation, that means 000, and 1 representation 001. So after 7, up to 7, it follows the decimal number system only. So next 1 increment is there. For 8, there is no 8 symbol in the octal number system. That is why it simply follows the 1 and 0. So 1 and 0. After 7, 1 and 0 in the octal system, but that is 8 in decimal number system. So likewise 9, so it follows the 11 sequence, like sequence 12, 13, 14, 15, 16, 17 up to 15. Now the 16 in decimal, which is represented in octal. So how we can represent? This is a, after 17 there is no again 18 in octal. So that is why we simply represented it as 20. So this is the representation for the octal number system corresponding to decimal number system. Coming to hexadecimal number system, so here the base is 16. Now uses 16 symbols. We already discussed it. So from digits 0 to 9, as usual it follows the decimal. And letters A to F. So these are the alphabets. So hexa means 6. So hexa means 6 means A to F. So A represented the 10 and B representation is 11, C representation is 12, likewise F representation is 15. So up to 15. So 0 to 15 so is the representation. So totally 16 numbers. So that is why 0 to 15 means totally 16. So this is called hexa plus decimal. So 6 plus 10. So totally 16. We call this one as a hexadecimal. That is why we call this one as a hexadecimal. So computers uses widely used in programming and memory addressing as one hexadecimal digit maps to 4 binary digits as usual. This is also simple representation. We can remember a huge binary number system to hexadecimal number system. Readability makes representing large binary values more concise and easier to read for humans. This is very simple again. So this is a simple hexadecimal number representation, decimal, binary, hexadecimal. So decimal you can observe in the left and binary in the middle and right is the hexadecimal. So binary is a representation of 4 bit representation in binary. So simply we can write the 1 in the hexadecimal. So likewise up to 9 we are representing the 9. So 1001 is the representation in the binary. And for 10, A means 10 in the decimal, and binary is 1010. So likewise it continues from 10 to 15. So this is the representation of 10 to 15. So A, B, C, D, E, F. This is the representation. If we get 13, simply the corresponding D is the representation. So after conversion of the decimal to binary or decimal to hexadecimal, if we get 13, so we can convert the 13 to D. So likewise we can represent the number systems in the hexadecimal. So here binary, this is a simple representation of all the 4 number systems what we discussed now. So binary, that is 2, base 2. So only 0 and 1 are the numbers we are using. And octal, 8 numbers, totally 8. So from 0 to 7 we are using in the octal number system. So decimal, so totally 10. So from 0 to 9 we are using. And hexadecimal, 16, 0 to F. We are already discussing in here. And not only these 4 number systems, there are so many number systems in our present days. So these are again comparison table of all the number systems, these 4 number systems. And not only those 4 number systems, these are other type of number systems. So this is, first one is decimal, second one is binary as usual for comparison, and third one is gray coding, and fourth one is BCD, and fifth one is XS3. So third one is gray coding. So gray coding, it is just following the switching, single switching. So that means 0000 is the first one and 0001 is the second one. That means there is a simple representation from 0 to 1. Now 0000 representation for decimal, that is 0. 0001 is the representation for 1. That is okay, fine. Now here if we observe, the last bit is only changing from 0 to 1. That means only one switching. All the 3 before all the 3, the 3 zeros are same. That means only one switching is happened here. Now from here to here, that means 1 to 2, 0001 to 0011. So now again this first 2 zeros are not switching, and the last one is also not switching here. Only the second position 0 is switching to 1. That means again a single switching here. Now from here to here, again 00 is not switching, same here, and at the same time this 1 is also not switching. That means 001 is same, 001 is same here, and last one is moved to 0, again one switching. So that means the definition is there is a one switching, but from one position to other, the next levels, that is the gray coding. And mostly this one is used in the K-map simplification, that we will check in the next slides. And BCD representation is binary coded decimal. So binary coded decimal is nothing but a single decimal representation is a 4-bit representation in the BCD. So that means 0, this is simply like a binary, up to 9, but coming to 10, so 10 is again a representation in BCD. So 4-bit representation. That means 1 is represented in 0001 and 0 is represented in 0000. So this is the representation for 10 in BCD. So likewise we have to follow so there is a 8-bit representation for 10, but up to 9 it simply follows the binary. Coming to XS3, so this is simple again. So 0, decimal is 0, so 0 plus 3, that is equal to 3. So this is the 3-bit representation. So 3 is the binary value. That means XS3 means plus 3. For every decimal value we simply add 3. So 3 plus 3, this is 6. So 6 binary representation is this one. So likewise 5 plus 3, that is 8. So 8 representation is this one, binary representation. That means simply the binary representation just incrementation of 3 plus 3. This is the XS3 system. Coming to the summary, in digital logic design, a number system is a way of representing numerical values using a set of symbols and a radix, that we call it as a base. The radix determines how many unique digits are used and how positional values are weighted. And commonly used number systems include decimal, which contains the base 10, binary, which contains the base 2, octal, which contains the base 8, and the hexadecimal, which contains the base 16. Each number is represented using a positional notation where the value of the digit depends on its position and the radix. The general form of a number is expressed as a weighted sum of the power of the base. And binary numbers are fundamentals to digital systems because they map directly to logic levels either 0 or and 1. Octal and hexadecimal systems provide a compact representation of long binary numbers, making them easier for humans to read and debug. So in order to remember the number of bits, we can easily represent this octal and hexadecimal. Thank you.